March 24, 1945. 5 kilometers south of Wesel, Germany, the Rhine River. Captain James McAdams pressed his field glasses to his eyes and watched German artillery shells explode 200 yards downstream. The water erupted in white columns that hung in the cold morning air before collapsing back into the current. It was 8:35 hours. Behind him, 25 GMC trucks idled in the tree line, each loaded with components that would become the longest treadway pontoon bridge ever constructed across a major river. McAdams lowered his glasses. The men of Company E and Company C, 17th Armored Engineer Battalion, were already moving toward the riverbank. They had 6 hours to do what the general said would take 2 days, and they would do it under fire. The Rhine represented more than a river. It was Germany's last natural barrier, 1,000 feet of dark water flowing north from the Alps, carrying the industrial runoff of a dying regime. On the far bank, what remained of the German 1st Parachute Army waited with artillery pieces and direct observation of every approach to the water. The morning reconnaissance had confirmed what everyone already knew. There would be no safe way to build this bridge. There would only be the necessary way. The 17th Armored Engineer Battalion belonged to the 2nd Armored Division, the unit known as Hell on Wheels. They had landed on Omaha Beach on D-Day. They had built bridges across the Seine. They had fought as infantry during the Battle of the Bulge when German panzers broke through the Ardennes. They had learned that combat engineering meant holding a wrench in one hand and a rifle in the other. Now they faced their greatest technical challenge of the war. A record-breaking bridge built at combat speed under direct artillery observation. McAdams had spent the previous 3 days preparing for this moment. The preparation process revealed everything about how American military engineering functioned in 1945. At Maastricht, his Company E had conducted intensive training with Company C of the 22nd Engineer Combat Battalion, who had no previous experience with treadway equipment. For 6 full days, McAdams's veterans shared their technical knowledge. They demonstrated how to inflate the massive pneumatic pontoons. They showed the precise method for lashing saddles to the floats. They explained the critical importance of anchor placement and weight distribution. This knowledge transfer represented a fundamental advantage of American military doctrine, the ability to rapidly disseminate specialized skills across units. The capacity to transform inexperienced soldiers into competent bridge builders in less than a week. The training had included full-scale rehearsals. Twice, the combined units built complete practice bridges across the Meuse River under simulated combat conditions. Engineers used artificial moonlight created by searchlights. Fob generators obscured visibility. Officers called out imaginary artillery strikes to create stress and urgency. The rehearsals taught men how to work in darkness, how to maintain focus under pressure, how to coordinate complex tasks when communication was difficult. McAdams had flown aerial reconnaissance over the actual Rhine crossing site with selected non-commissioned officers. They studied the terrain, memorized the approaches, identified potential assembly areas. This level of preparation was characteristic of American military operations in late 1944 and 1945. Meticulous planning combined with rapid execution, industrial thoroughness applied to military objectives. The strategic context was vast and unforgiving. Operation Plunder, the massive Allied crossing of the Rhine, had begun the night before with 4,000 artillery pieces firing for 4 hours straight. British and Canadian forces had crossed near Ries. American paratroopers from the 17th Airborne Division were dropping east of Wesel at this very moment. The sound of their aircraft still droned overhead. Field Marshal Bernard Montgomery had planned this operation for months. Every division, every corps, every army group depended on bridges. Steel and pneumatic rubber stretched across water. Without bridges, tanks could not cross. Without bridges, supplies could not flow. Without bridges, the Wehrmacht had time to reorganize and counterattack. The capture of the bridge at Remagen 2 weeks earlier had demonstrated the strategic value of Rhine crossings. On March 7, troops from the 9th Armored Division had reached the Ludendorff Bridge and found it still standing, one of the only bridges the Germans had failed to destroy. American soldiers rushed across under fire. Engineers from the 291st Engineer Combat Battalion worked frantically to dismantle German demolition charges. The bridge held long enough for 6 divisions to cross. Then it collapsed on March 17, killing 28 engineers and wounding 93. But by then, the Americans had built pontoon and treadway bridges on either side of the damaged structure. More than 125,000 troops had established a bridgehead on the eastern bank. The lesson was clear. Bridges were worth dying for. Bridges shortened wars. But Remagen had been 300 feet long. The bridge McAdams needed to build would be nearly 4 times that distance, and there would be no existing structure to use. His engineers would create it from nothing, from components prefabricated in woods a few miles back, from 18-ton pressurized rubber pontoons and 12-foot sections of steel treadway track. Lieutenant William Doibel from Kansas City stood at the assembly point and watched his men unload the first pontoon float. The thing was massive. A rubberized bag inflated with air compressors, supporting a saddle made of metal and plywood. On that saddle would rest the treadway sections, each weighing more than 500 pounds, each requiring 4 men to carry and position. Doibel understood the mathematics of what they were attempting. To cross the Rhine here required 80 to 90 complete sections. Each section consisted of a pontoon float, a saddle assembly and treadway tracks. Each section had to be perfectly aligned with the previous section. Each connection point represented a potential failure mode. A single weak link would compromise the entire structure. The M2 treadway bridge system represented American industrial capability translated into military engineering. The design philosophy was revolutionary in its simplicity. Previous military bridges required specialized equipment, trained crane operators, heavy machinery that was difficult to transport and deploy. The M2 system eliminated all of that. Every component was designed to be carried and assembled by infantry soldiers with basic training. The pontoons were inflated with standard air compressors. The saddles bolted together with hand tools. The treadway sections connected with large steel pins that men hammered into place with sledgehammers. No cranes needed, no specialized vehicles required, just manpower and determination. The genius of the system lay in its modularity and scalability. Engineers could build a bridge of any length by adding more sections. They could increase load capacity by doubling or tripling the number of pontoons supporting each treadway segment. They could adjust to varying river widths, different current speeds, changing tactical requirements. The flexibility was unprecedented. A single battalion could carry enough components to bridge multiple rivers on a single advance. This capability fundamentally altered the pace of armored warfare. American divisions no longer had to wait days or weeks for specialized bridging units to arrive. They carried their own crossing capability with them. The pontoon technology itself was remarkable. Each float was constructed from heavy rubberized fabric, reinforced with internal baffles. When fully inflated, the pontoon could support 18 tons while maintaining structural integrity even if punctured by small arms fire. The rubber was resistant to petroleum products, which meant the pontoons could operate in water contaminated by fuel spills from destroyed vehicles or damaged bridges. The inflation valves used standardized fittings compatible with every air compressor in the American inventory. This standardization meant engineers could use equipment from any unit, any supply depot, any captured German facility with compatible machinery. The saddle assemblies were equally well designed. Each saddle consisted of a metal frame with plywood decking that distributed weight across the pontoon surface. The saddles attached to the pontoons with canvas straps and metal buckles that could be adjusted for proper tension. This adjustability was critical. As pontoons settled under load, engineers could tighten or loosen the saddle attachments to maintain proper weight distribution. The system was self-correcting within reasonable parameters. It accommodated operator error and environmental variation without catastrophic failure. The treadway sections themselves were engineering marvels. Each 12-foot section was constructed from heavy steel planking with raised ridges that provided traction for vehicle tires. The steel was treated to resist corrosion from river water and road salt. The edges of each section featured precisely machined holes for the connection pins. When properly aligned, 2 sections would mate together so tightly that water could barely seep through the joint. The result was a roadway surface almost as smooth as pavement, capable of supporting tanks traveling at moderate speed without damaging the structure. Technical Sergeant Gordon Ketchpaw moved along the riverbank with his squad, identifying anchor positions. Every pontoon float needed upstream and downstream anchors to hold it against the current. The anchor system was another example of elegant engineering. 200-pound mushroom anchors upstream, 100-pound anchors downstream on alternating floats. The anchors dropped to the riverbed on steel cables that passed through guides on the pontoons. When properly positioned, the anchor cables created a web of tension that held the entire bridge structure in place against the Rhine's powerful current. Ketchpaw had calculated that 93 pontoon floats would require 216 anchors. Each anchor had to be positioned correctly, or the entire bridge would swing loose and be carried downstream. The anchor placement required intimate knowledge of river hydraulics. Anchors too close to the pontoons would not provide adequate holding power. Anchors too far upstream would create excessive cable angle and reduce effectiveness. The optimal position depended on water depth, current speed, riverbed composition, and the weight distribution of vehicles crossing the bridge. The riverbed here presented specific challenges. Aerial reconnaissance and previous intelligence reports indicated a mix of sand, gravel, and clay. The sand provided poor holding, meaning anchors would drag if not properly sized. The clay offered better grip but required different anchor designs. Ketchpaw's experience told him to err on the side of heavier anchors and shorter cable runs. Better to over-engineer the anchor system than watch the entire bridge swing downstream when the first tank attempted to cross. At 0845 hours, the first artillery shell hit the assembly area. The explosion sent men diving into the mud. Shrapnel tore through tree branches overhead. When the smoke cleared, 3 engineers were wounded. Medics ran forward with stretchers and medical bags. One man had shrapnel in his leg, another had been hit in the shoulder, the third had a head wound that bled profusely but appeared superficial. The medics applied pressure bandages, administered morphine, and evacuated the wounded to the battalion aid station set up 500 yards to the rear. The work continued without pause. There was no stopping once it started. Every minute mattered. Every delay gave the Germans time to register more artillery on the site. The German artillery doctrine in March 1945 was predictable in its desperation. With most of their forward observers killed or captured, German gunners relied on pre-registered coordinates and occasional observation from high ground positions. They fired in patterns, walking rounds across known assembly areas and obvious crossing points. The shelling was not particularly accurate, but it was persistent. A constant harassment that forced engineers to work with the knowledge that death could arrive without warning. The smokescreen that had covered the area earlier was lifting. German observers on the far bank could see everything now. The lifting smoke represented a critical moment. McAdams knew his window of relative safety was closing. Once the Germans had clear observation, their artillery fire would become more accurate and more deadly. The only counter was speed. Build faster than the enemy could effectively target the construction. The engineers worked in a rhythm born from repetition and necessity. Pontoons were inflated and saddles lashed on top. Treadway sections were carried to the water's edge. Power boats pulled the assembled sections out into the current. Men waded into the Rhine, water up to their chests, guiding the pontoons into position. The cold bit through their uniforms. March in Germany meant near-freezing water temperatures. Hypothermia was as much a threat as enemy fire. The water temperature in the Rhine in late March typically hovered just above 40 degrees Fahrenheit. At that temperature, unprotected soldiers could maintain function for perhaps 20 to 30 minutes before hypothermia began to degrade performance. After an hour, even the strongest men would lose coordination and mental acuity. The engineers rotated crews constantly. Men would work in the water for 15 minutes, then rotate to shore duties for 30 minutes to warm up. This rotation maintained operational efficiency while preventing cold water casualties, but the rotation system created its own challenges. It meant that crews were constantly changing positions. Men who had been working at the bridge terminus would rotate to shore assembly. Men from shore assembly would move to pontoon guidance. The constant rotation required exceptional coordination and clear communication. Squad leaders had to track which crews were cold, which were fresh, which had specific technical skills needed at critical points. The rotation added complexity to an already complex operation. Private First Class Kenneth Hanna worked at the bridge assembly point, connecting treadway sections with his squad. The steel was heavy and awkward. Each section had to be aligned perfectly before the pins could be driven through. The alignment process was more art than science. Hannah would sight down the length of the treadway, looking for the precise moment when the holes in adjacent sections lined up perfectly. Too high and the pin would bind, too low and the connection would be weak. The margin for error was perhaps a quarter inch across a 12-foot span. Once aligned, the pins had to be driven through both sections with sledgehammers. The pins were solid steel, 2 inches in diameter, 16 inches long. Driving them required precise hammer strikes that pushed the pins straight through without bending. A bent pin was worse than useless. It would jam in the hole and have to be cut out with torches or hacksaws, costing precious minutes. Hannah had developed a rhythm. 5 heavy blows to drive it halfway. 3 more measured strikes to seat it flush. The rhythm kept him focused and prevented mistakes. Behind him, another shell exploded. The concussion wave traveled across the water. Hannah felt it in his chest but did not stop working. There was nothing else to do. Stop, and the bridge did not get built. Stop, and the tanks could not cross. Stop, and men died later instead of now. This was the mental calculation that sustained combat engineers. The work itself was dangerous and exhausting, but not doing the work meant other soldiers would face danger without support. Better to risk yourself building infrastructure than to let infantry advance without supply lines. The German artillery fire came in waves, sometimes sporadic, sometimes concentrated. The enemy had forward observers somewhere in Wesel or on the high ground to the east. They were calling corrections, walking their fire across the construction site. The German artillery batteries were likely positioned 3 to 5 miles behind the front lines, beyond the range of American counter-battery fire. They were probably using 105mm or 150mm howitzers, standard Wehrmacht field artillery pieces. At that range, accuracy was limited, but volume compensated. The Germans would fire several rounds, observe where they landed, adjust, and fire again. The process was methodical and deadly. When the smoke screen lifted completely around D900 hours, the shelling intensified dramatically. One assembly point took 3 direct hits in rapid succession. The explosions destroyed 1 partially assembled pontoon section and wounded 2 more engineers. McAdams immediately ordered that assembly point moved several hundred yards upstream. Engineers grabbed their equipment and ran. Pontoons were partially deflated and dragged to new positions. The work continued with barely a pause. The ability to adapt to changing conditions was critical. Rigid adherence to the original plan would have resulted in unnecessary casualties. Company C worked alongside Company E with mechanical precision. These were not fresh troops. These were combat veterans who had seen every kind of hell the European theatre could provide. Many of these men had been with their units since the North Africa campaign in 1942. They had built bridges under fire in Tunisia. They had crossed the Mediterranean for the invasion of Sicily. They had landed in Normandy and fought through the hedgerow country of France. They had been at the Siegfried Line and in the frozen forests of Belgium during the Battle of the Bulge. They understood that engineering in combat meant accepting casualties as the price of forward movement. The experience of these veterans manifested in countless small ways. They knew how to dig fighting positions while simultaneously assembling equipment. They understood which sounds meant incoming artillery and which were outgoing friendly fire. They could distinguish between German and American aircraft by engine noise alone. They worked with the efficient movements of men who had performed these tasks dozens of times under similar conditions. There was no wasted motion, no hesitation, no confusion about roles and responsibilities. Each man knew his job and trusted his squad mates to know theirs. The pontoons rode high in the water, held in place by anchor lines that stretched down to the riverbed. Each section connected to the next with the heavy steel pins driven flush into their housings. The treadway surface was solid enough to support vehicle traffic. Men walked on the completed sections, checking connections, looking for weak points. The structure flexed slightly with the current but held firm. The engineering was sound. The construction was proceeding faster than anyone had predicted, but there were still more than 800 feet to go. The Rhine current worked against them constantly. The river was flowing at approximately 3 miles per hour, carrying debris and silt from upstream. This current created tremendous lateral force on the pontoons. Each float acted like a sail, catching the current and trying to swing downstream. The anchor cables resisted this force, but the resistance created enormous tension on every connection point. The engineers had to account for this tension when positioning pontoons. Each float had to be placed slightly upstream of its final position, so that when the current caught it and the anchors held, the float would swing into perfect alignment with the existing bridge structure. The powerboats that pulled the pontoon sections into place struggled against the flow. These boats were small military craft with gasoline engines, capable of perhaps 15 miles per hour in calm water. Against the Rhine's current while towing a massive pontoon section, their effective speed dropped to perhaps 5 miles per hour. The boat operators had to maintain precise throttle control, keeping enough power to fight the current without creating so much wake that they destabilized the pontoons they were towing. It was skilled work that required both technical knowledge and practical experience. Men in the water guided the sections by hand, fighting the current, their hands numb from cold. One engineer lost his footing on the slippery riverbed and was swept downstream. He managed to grab an anchor line and pull himself back to the construction site. His squad leader immediately rotated him to shore duty to prevent hypothermia. Another man took his place in the water. The rotation continued without discussion. Everyone understood the system. Everyone accepted the necessity. Captain McAdams moved along the bridge, checking progress, talking to squad leaders, making adjustments. His command style was direct and practical. He did not give inspirational speeches or attempt to motivate through rhetoric. He commanded through competence and personal example. When a critical connection point was failing, McAdams was the one who climbed into the water to help position the pontoon correctly. When a squad was falling behind, he joined them and worked alongside until the problem was resolved. His men respected him because he understood their work and never asked them to do anything he would not do himself. McAdams had flown aerial reconnaissance over this site days earlier with his company executive officer and several senior sergeants. They had studied the terrain from 5,000 feet, memorizing landmarks, identifying approach routes, noting potential problems. He knew where the riverbed was shallowest and therefore where anchors would be most effective. He knew which section of the far bank provided the best exit point for vehicles leaving the bridge. He knew where German artillery observers were most likely positioned and could anticipate their fields of fire. This knowledge accumulated into tactical advantage. Preparation compensated for the chaos of combat. At 1100 hours, a German artillery shell hit directly in the water 50 feet from the bridge. The explosion created a geyser that drenched the nearest work crew. Shrapnel cut through the air with a distinctive buzz of high-velocity fragments. One man went down, his leg torn open from knee to ankle. The wound was serious, but not immediately life-threatening. The femoral artery was intact. Medics pulled him from the water and carried him to the aid station. Battalion surgeon Captain James Mills took one look at the wound and began cutting away the man's trousers to expose the injury. The shrapnel had created a long, ragged laceration that would require extensive debridement and possibly surgery, but the man would survive if infection could be prevented. Mills and his medical team had set up their aid station in a partially destroyed building 300 yards from the river. The location was close enough to provide rapid treatment for casualties, but far enough from the bridge site to avoid the heaviest artillery concentration. The aid station operated continuously throughout the bridge construction. Wounded men arrived in a steady stream. Some had shrapnel wounds. Others suffered from concussions caused by nearby explosions. A few showed early signs of hypothermia from prolonged exposure to cold water. Mills and his medics treated each man, made triage decisions, and evacuated the seriously wounded to field hospitals further to the rear. The medical support structure represented another American advantage. Every combat engineer battalion included an organic medical detachment with trained surgeons and corpsmen. Casualties received professional medical care within minutes of being wounded. This rapid treatment dramatically improved survival rates. German casualties, by contrast, often waited hours for medical attention. Their medical infrastructure had been shattered by 3 years of retreat and attrition. This disparity in medical care was a force multiplier. American soldiers fought more aggressively when they knew wounds would be treated quickly and competently. The rest of the crew kept working. There was a rhythm to it now. Work until the shells came in. Take cover if possible. Resume work immediately. The bridge grew longer with each passing hour. The far shore was still distant, but no longer impossibly far. The engineers began to believe they might actually complete this bridge within the planned time frame. The belief system that sustained these men was pragmatic rather than idealistic. They were not fighting for abstract principles or political ideologies. They were fighting to finish a specific task that would enable other units to advance. The mission was tangible. Build a bridge 1,152 feet long capable of supporting 60-ton vehicles across the Rhine River. Either they succeeded or they failed. There was no ambiguity. This clarity of purpose created extraordinary motivation. Every man understood exactly what was required and exactly what his role was in achieving that requirement. The technical achievement was profound and largely invisible to anyone not trained in military engineering. Each component of the M2 treadway system was designed with brutal simplicity: steel that could be mass-produced in American factories, rubber that could be vulcanized using standard industrial processes, connections that could be made with hand tools available in any hardware store. The system embodied American industrial philosophy: design for manufacturability, design for maintainability, design for use by minimally trained operators under adverse conditions. These principles, applied systematically across every weapons system and piece of equipment, created cumulative advantage that proved decisive. By 1200 hours, the bridge extended 600 feet. The far shore was still more than 500 feet away. German artillery continued to fall. One shell damaged 2 pontoon floats near the assembly point. The explosion punctured the rubberized fabric, causing rapid deflation. Engineers immediately disconnected the damaged floats using the quick-release mechanisms built into the saddle attachments. New floats were inflated and positioned. Fresh saddles were lashed into place. New treadway sections were connected. The repair consumed 30 minutes but did not stop forward progress. Other crews continued working at the bridge terminus while the damaged section was being replaced. This parallel processing of multiple tasks simultaneously was characteristic of American operational doctrine: never stop completely, always maintain forward momentum somewhere in the system. Lieutenant Deubel supervised the repair work with terse efficiency. His men knew their jobs and required minimal direction. Deubel's role was coordination rather than instruction. He ensured the right equipment reached the right location at the right time. He monitored the overall progress and identified bottlenecks before they became critical. He maintained communication with Captain McAdams and reported status updates every 15 minutes. This systematic approach to command and control enabled complex operations to proceed smoothly even under combat conditions. At 12:30 hours, a significant problem emerged. The riverbed composition in the center of the Rhine differed from the banks. The sandy bottom provided poor anchor holding. 2 anchor lines had dragged their anchors downstream, causing the bridge to develop a noticeable bow. If left uncorrected, the bow would eventually cause structural failure. Sergeant Ketchpaw identified the problem immediately and ordered heavier anchors deployed at the affected locations. Engineers in boats positioned 300-pound anchors at precise coordinates calculated to counteract the current force. The heavier anchors bit into the riverbed and held. The bridge straightened. Crisis averted through technical knowledge and rapid response. This incident illustrated a fundamental truth about military engineering: problems were inevitable. Success depended not on avoiding problems, but on solving them faster than they could cascade into failure. The American military system in 1945 excelled at rapid problem-solving because it empowered non-commissioned officers and junior officers to make decisions without waiting for approval from higher headquarters. Sergeant Ketchpaw did not need to radio battalion headquarters and request permission to deploy heavier anchors. He assessed the situation, determined the solution, and implemented it. This decentralized decision-making created operational tempo that German forces with their more rigid command structures could not match. By 1300 hours, enemy small arms fire began. German infantry on the far shore opened up with machine guns and rifles. The range was long, perhaps 600 yards, but the fire was accurate enough to be dangerous. Engineers working at the bridge terminus started taking rounds. Bullets snapped past, creating distinctive cracks in the air. One man was hit in the shoulder. Another had his helmet torn away by a near miss. The wound to the shoulder was clean, in and out, missing major blood vessels. The engineer whose helmet was struck was uninjured but badly shaken. Both men were rotated to rear duties. Return fire came from American infantry who had been positioned along the western bank specifically to provide covering fire. M1919 Browning machine guns opened up, their distinctive firing rhythm echoing across the water, tracers arced toward the German positions. The American infantry had no specific targets, but they fired suppressive patterns designed to make the German shooters keep their heads down. The volume of fire was sufficient to reduce the German shooting accuracy. Engineers at the bridge terminus could continue working, though they moved with greater caution and awareness. The arrival of small arms fire indicated the Germans were becoming desperate. Artillery fire alone had failed to stop the bridge construction. Now they were resorting to direct fire weapons that were far less effective at this range. The German infantry on the far bank were probably remnants of units shattered during the Allied bombardment the previous night. They were fighting because retreat was not an option and surrender not yet acceptable. Their resistance was determined but ultimately futile. They lacked the firepower to significantly slow the bridge construction, and they had no reserves available for counterattack. The engineers were exhausted but driven by the knowledge that completion was near. Muscles screamed. Hands bled from handling rough steel and cable. Uniforms were soaked with river water and sweat despite the cold. But the work continued, each pontoon positioned, each saddle secured, each treadway section connected. The bridge reached toward Germany like a physical manifestation of American will. The psychological effect of this approaching completion was significant. Men who had been working for nearly 5 hours without rest found reserves of energy they did not know they possessed. The end was visible. The far shore was close. Finishing the mission became personal, not because of orders or duty, but because of pride. They had come this far under fire. They had built something extraordinary under impossible conditions. Now they would finish it. At 100 hours, the bridge reached 850 feet. Only 300 feet remained. German artillery fire had killed no one yet, but had wounded 20 engineers. Several of those men had returned to duty after receiving medical treatment. Others were evacuated to field hospitals. The casualty rate was acceptable by military standards, but devastating by human standards. 20 young men torn by shrapnel, 20 families who would receive telegrams, 20 soldiers who would carry scars for the rest of their lives. This was the cost of forward movement in industrial warfare. At 4:30 hours, the smokescreen lifted completely. German observers had full visibility of the construction site. Artillery fire intensified immediately. Shells walked across the bridge site in a pattern that showed the enemy gunners had excellent target registration. This was the most dangerous phase of the operation. The Germans could see exactly where to shoot. Their corrections would be accurate. The only defense was speed. Captain McAdams made a critical decision. He pulled men from assembly areas and concentrated every available engineer at the bridge terminus, maximum manpower at the point of completion. The change in allocation meant pontoon preparation slowed, but assembly at the bridge accelerated. McAdams calculated that faster completion outweighed the risk of running out of prepared pontoons. His calculation was correct. The bridge extended rapidly, 900 feet, 950 feet, 1,000 feet. At 15:30 hours, one shell hit directly on a pontoon float near the center of the bridge. The explosion tore through the rubber, deflating the pontoon instantly. The treadway section it supported collapsed into the water. For a moment, it appeared the entire bridge might fail. The loss of support created stress on adjacent pontoons. But the engineering was sound. The structure flexed and redistributed the load. Adjacent pontoons settled lower in the water but held. Engineers swarmed the damage point. They disconnected the destroyed pontoon. A replacement was already being positioned. Within 45 minutes, the repair was complete. The bridge was whole again. This repair under fire demonstrated the robustness of the M2 treadway system. The modular design meant individual components could fail without catastrophic results. The structure was inherently redundant. Destroying a single pontoon did not destroy the bridge. This fault tolerance was engineered into the design deliberately. American engineers understood that equipment used in combat would be damaged. Systems that failed completely when damaged were useless. Systems that degraded gracefully while remaining functional were invaluable. The far shore was now within reach. Company C took over the final sections. They worked with intense focus, knowing the end was near. Each pontoon was positioned with extra care. Each connection was double-checked. The last 300 feet took longer to build than the previous 300 because precision mattered more than speed now. A mistake at this stage could compromise the entire structure. At 15:45 hours, engineers positioned the final pontoons. The gap between the bridge and the far shore narrowed to 50 feet, then 25 feet, then 12 feet. At exactly 100 hours, Technical Sergeant Gordon Ketchpaw personally hammered the final connection pins into place. The last treadway section was bolted down. The bridge reached from the western bank to the eastern bank. 1,152 feet of floating roadway stretched across the Rhine River, the longest treadway pontoon bridge in the world, built in 6 hours and 15 minutes, built under constant artillery fire, built by men who understood that speed was survival. The first vehicle across was a 2.5-ton truck from the 30th Infantry Division. The driver approached cautiously, testing the bridge surface with the front wheels before committing fully. The truck rolled onto the treadway at 1600 hours exactly. The pontoons settled under the weight but held firm. The truck drove across at moderate speed, its tires humming on the steel surface. German artillery shells fell around the bridge but did not hit the structure. The truck reached the far shore. Infantry soldiers on the eastern bank cheered. Behind the first truck, more vehicles queued up. Tanks, armored personnel carriers, supply trucks, artillery pieces. The entire weight of the American advance in this sector depended on this bridge. The human cost was visible in the faces of the engineers. They were not celebrating, they were collapsing. Lieutenant Doibel stood at the western approach and watched the vehicles cross. He was utterly exhausted. His uniform was soaked with river water and mud. His hands were cut and bruised from handling steel and rope. Around him, his men sat or lay in the mud, too tired to stand. They had done something extraordinary, and they knew it. They had broken every existing bridge-building record. They had worked under fire without stopping. They had created infrastructure that would enable victory. But at this moment, they were simply men who had pushed themselves beyond normal human limits and needed rest. Captain McAdams walked the length of the bridge one final time, checking every connection, looking for any weakness that might cause failure when heavy vehicles crossed. His inspection was thorough and professional. He found no critical problems. The bridge was well built. His men had performed magnificently. McAdams allowed himself a moment of satisfaction before returning to his command post to write his after-action report. There were still tasks to complete. The bridge required guards to prevent sabotage. Maintenance crews needed to be assigned for continuous inspection and repair. Approach roads had to be improved to handle the increased traffic. A combat engineer's work never ended. But they had accomplished the primary mission. The Rhine could be crossed, the advance could continue, the war could be shortened. That was enough.